Morning, lesson 10. And lesson 10 is about the nucleus. We're talking about radioactivity, fission and fusion, the three processes whereby we make a nucleus more stable. Now they're all slightly different, so we need to be clear on what the differences are. So radioactivity is spontaneous, it just happens. Okay, you don't have to bombard with neutrons, you don't have to apply a large force, these things just happen. So you have a huge number of unstable nuclei, and every second a certain fraction of them decay, okay, spontaneously. You don't know which one's going to decay, it's spontaneous, but with a large number of nuclei, you will know that a certain fraction will decay every second, okay, that's we call the decay constant, and which we'll come back to later on when we're doing the maths on paper. Right, so let's just take an example, okay, of it, and let's take a beta decay that we've looked at before, which is the beta decay of carbon 14. Okay, so we're going to use model, okay, we're going to use these geomags because we don't have anything else, okay, we're going to use these geomags as models, okay, and a geomag, what we're going to have is we're going to have 6, in this case we have 6, the grey ones are the protons and we've 8 neutrons, so that's your carbon 14 nucleus. Now does it make sense? Okay, we have 6 protons, okay, so it's atomic number 6. We have a total of 14 protons and neutrons, they're kind of called nucleons if you want, okay, so we have 14 of those, so that's your carbon 14. Right, now what happens, okay, in beta decay, okay, quite bizarrely, is that a neutron, one of the neutrons here, okay, so there it is, one of the neutrons, that neutron magically, or not magically, but that neutron changes into a proton. So I've replaced a neutron with a proton, effectively is what I've done. Okay, and there we go. Right, so now let's look at it. We have 1, 2, 3, 4, 5, 6, 7 protons now. So the mass number, so it's spontaneous, so nothing else happening. So afterwards we have 7, which means it must be nitrogen. And if we count up, we still have 14 because we've lost a neutron, but we've gained a proton. So there's no change in the mass number. That should be beginning to make sense to you at this stage. Okay, what also happens is being emitted, okay, is an electron. Okay, so there's an electron being emitted as well, not to scale, 2,000 times smaller in reality. So electron is being emitted, and there's also a neutrino. Okay, remember, but that's it. And there is some release of energy because it's more stable. Okay, less energy now required to bind the nucleus together. It is more stable. So some energy, but you're not talking about a huge amount of energy. But that manifests itself, you know, and that things can glow with radioactivity and so on. There will be some energy released. If we're looking for big energy, we move on to fission and to fusion. Okay, so that's that one. We move our what is now our nitrogen nucleus out of the way and get rid of the electron. And we're going to move on now and we're going to look at fusion and fission. So remember the problem, okay? And down here, over here, look, okay, I don't have the right colours, but that's the correct number of protons and neutrons for iron. So that's the magic size. You want your nucleus to be that size, okay? In the stars and the sun, okay, you get, this is one of the fusion reaction that happens, okay, you have, okay, so look at this one, okay, it is hydrogen because it has only one proton and it has one neutron, okay, so let's write it. So it's hydrogen, 1, mass number 2, okay, and we've a second one there, okay, same thing, okay. Now that's, okay, so they're called hydrogen 2, but they have their own special name, we call it deuterium, okay, and remember hydrogen 3, tritium, okay. But what happens is, okay, and some of you got caught with this in the assignment, okay, is that it forms another, an isotope of, sorry, it forms an isotope of helium and a neutron. Okay, so basically they join together. Now to get them to join together, that's the huge problem with fusion. They're both positively charged. You have 2 positively charged nuclei, you're trying to move them together, so you need a huge force to bring them together to overcome the electromagnetic force, okay, and to get them close enough that the strong force kicks in. Okay, so you need a huge force to get them into the region where the strong force happens. That's the problem with fusion. A huge initiation energy is required. Okay, so but what happens is you hammer them together, but what eventually happens is you end up with a neutron, okay, and a helium nucleus. Now it's a helium nucleus because you have 2 protons. Okay, so we have a helium with 2 protons. It has 1 neutron, so it's 2, 3. And so we wrote down 2, 4 for that. Remember, isotopes of helium, they don't all have to be the same as alpha particles. They could be He3, He4, and maybe something else. And the neutron, remember neutron? No charge or no atomic number of protons, so N, 0, 1. And that's it, okay? So, but let's recap on fusion. The big problem with fusion is that you need a huge energy to get the nuclei together to overcome the electromagnetic force. But when you get them close enough together, the strong force kicks in and the strong force holds it together. It's more stable than the two separately, so there is a huge release of energy then. And the release of energy can cause further fusion. So you need to get it going. Once it gets going, it'll keep going. And that's what happens in stars. That's what happens in stars. But that's why we don't have fission reactors to make electricity at the moment. That's the issue. Okay, so that's that one, all right? So that's your fusion. So remember, you need to supply energy. It's not the same as radioactivity. And remember, what you're trying to do is you're making the nucleus more like iron. No, it's not much more like iron, but it's getting bigger. It's getting there. And that process actually continues, okay? That process continues. We don't really go into detail. Right, okay, so we put that out of the way, and now we go to the great crack. Now, okay, with this one. Okay, now, I didn't have enough geomegs. Okay, I didn't have enough geomegs, okay, to make one that's actually valid, but so this is a little bit small. This is a little bit small, okay, so, but you can see, this is a very large nucleus, and we have a problem, okay, so watch what happens in fission, and just to be clear on it, okay, so what happens in fission is you get another neutron, like that, and you get the neutron to join that nucleus. So you need slow neutrons, and we'll see that when we do the fission reactor tomorrow. You need slow neutrons. You don't need fast neutrons, and we'll come back to that in a sec, okay? And what happens is, a slow neutron joins this nucleus, and this nucleus was unstable already, but now it's become more unstable. Okay, it's become more unstable, a bit like Jenga. This is the straw that breaks the camel's back, okay? And what happens then, okay, what happens then is that this nucleus becomes unstable and basically becomes that shape, okay, and then eventually splits, okay, into two, and this is important, remember from your definition, two similar size nuclei, not a big one or a small one, two similar size nuclei, and that's important, okay, but also emitted, okay, will be 3 neutrons, okay, 2 or 3, depends. So this is what happens after. So remember what happened, the neutron joined, made the unstable nucleus too unstable. The unstable nucleus eventually broke into 2 similar size bits, but also more neutrons. Now the neutrons emitted here are going fast. They're called fast neutrons. For them to cause more fission, we need to slow them down, and we'll see in the fission reactor tomorrow how we slow them down. We use a thing called a moderator. All right? But that's your fission. And once again, okay, it's not spontaneous. We had to supply the neutron to make it too unstable for it to split. Energy is released again, okay, because the energy needed to make all of these is less than the energy needed to hold the whole unstable thing together. Okay, so energy is released, and it is becoming, and this one looks better, okay, these are clearly becoming more iron-like, okay, the nucleus is getting smaller to become more iron-like, okay, and that's that one, okay, so that's the second scenario, or the third scenario. So we have radioactivity, we have fission, and we have fusion. Okay, thanks.